Yes, I'm from Johns Hopkins University Applied Physics Lab in Maryland. Um, and I'd like to tell you about our tunable transmissive IR filters. So the motivation here is for standoff chemical detection in the atmosphere, which is based on IR spectral sensing. So this is commonly performed with a hyperspectral imager, and the principle is that different chemicals have characteristic emission bands in the IR spectrum, and if you can detect those emission bands in a scene, you can determine which chemicals are present in a particular scene. So there's a couple of examples here from literature of, for example, methane emission from a lake, the sulfur dioxide cloud emitted from a cruise ship. This is sulfur hexafluoride and ammonia simultaneously released into the environment. All of these things you can detect with a hyperspectral imager, which is great. However, hyperspectral imagers currently available are relatively large, bulky, heavy, and they produce massive amounts of data. So we would like to keep this sort of chemical detection capability using IR spectral sensing, but come up with ways to make the system a lot smaller and less power hungry so that it can be deployed on, for instance, UAVs or unattended ground sensors, that sort of thing. So how will we do this? Our concept is to provide a set of spectral filters that can be switched on and off depending on which chemicals you're trying to detect. And you put this set of spectral filters in a single plane that's off of the focal plane. It's not in the focal plane of your scene. And you turn on the filters that you want to transmit for the particular chemical of interest, turn off the others, take an image, and you should be able to quickly see if the gas of interest is present by what pops out as bright in the scene. So how are we going to do this? Metasurfaces are a promising approach for making reconfigurable filters, especially in a single plane, because the frequency of the metafilter can be tuned via geometrical parameters that can be defined lithographically. However, transmissive tunable metafilters are relatively difficult to make. The fact that, that you want to make a transmissive design for an imaging system is important, but it limits your materials choices somewhat, which also limits your tuning options. So we came up with a design to tackle this problem, to make a tunable transmissive metafilter that can be switched on and off using a MEMS device. The way it operates is as follows. We have two separate metastructured layers that are separated by an air gap. The bottom layer is on top of a germanium substrate. The top layer is sandwiched between two thin film layers of silicon, and there's an air gap in between them. These are identical metastructures nominally. They have the same feature size and dimensions, and this is what the unit cell of the metastructure looks like. So you get a lot of repeating increments of this inverse cross in a gold layer. And the dimensions of the cross and the spacing define your transmission frequency, your wavelength at which you get high transmission. The materials that the cross is in contact with modulate that frequency somewhat. So the silicon sandwich on the top metastructure shifts the transmissive peak of this top metastructure away from the transmissive peak of the bottom metastructure. So you get, in effect, zero transmission when you have a gap of a micron or so. That's the blue line here. And then as you apply a voltage and bring these two surfaces into contact, you get slightly higher transmission as they come closer, but you don't get large transmission until they're in contact. Once they're in contact, this bottom silicon layer is able to modulate the frequency of the bottom metastructure in the same way that the frequency is being modulated on the top metastructure. Your two transmission bands overlap and you get high transmission. So we started off making single layer metastructures These are patterned using electron beam lithography, feature sizes on the order of 200 nanometers or so, dictated by the wavelength bands that we want to operate in, the midwave and the long wave IR. And you see the results of some of our various types of designs here. This one operates around 4 microns. If you put silicon on top of it, you can see the peak shifts a little bit to the right, and the same thing here. So then we moved on to fabricating the full MEMS device. This is a picture of the repeating unit cell metastructure on this on the center of this MEMS beam. So that's located right here. The beam is fixed here at the two ends. You can actuate it with a voltage between the substrate and the metal beam, suspended beam layer here. And there's a stationary metasurface underneath the beam that you can't see in the image because it's hidden by the beam as well. So when we actuate these, as I said before, you apply a voltage, and as you apply the voltage, the beam pulls in. So this is optical profilometry measurements of the beam height. So red is high and blue is low. So the beam is suspended above the substrate initially at 0 volts, and so is the metasurface. You see some wrinkling in the metasurface due to residual stress. As we apply increasing voltage, you can see the metasurface becomes more blue. It's moving down, and we reach full pull-in for this device at 44 volts. You can see that in a little better detail here. This is a line scan across just the center section of the beam, the metasurface section. So you can see initially at 0 volts, there's some buckling due to stress that we could use some optimization for, stress optimization for, to decrease that in future iterations. At 23 volts, we do achieve pull-in at a single spot here, and then at 44 volts, you've got essentially complete pull-in. So how does this work as a spectral filter, a tunable spectral filter? In short, it didn't work exactly as we designed it. And this is due to some tolerances in the fabrication process. But we did get some tunability, and I think we have indications that if we improve the fabrication process, we should be able to get the designed performance. But this is what we got in our first iteration of devices at 0 volts. You see this double peak structure. This is from the top metasurface, the suspended metasurface, and this is from the stationary metasurface on the bottom. This second peak here, by design, should be over here. So our fabrication tolerances shifted the peak to the right, and the peaks are too close together to get destructive interference, and we end up getting a relatively high transmission at 0 volts. As we increase the voltage, the two peaks move further apart, and we decrease our transmission. And we also have the effect of decreasing the bandwidth because of these initially partially overlapping peaks. So this is sort of the opposite of the designed mode of operation. And we're looking to improve that in the future with improving fabrication tolerances. However, I alluded on the last slide that we have seen some indication that we can get the as-designed performance if we improve our fabrication process, and this comes from devices on the wafer. We made several hundred devices on a single wafer. A few of them did not work, did not operate in terms of the MEMS actuation. They were either stuck in the down position or stuck in the up position. And we did find one stuck in the down position that has the designed narrow band and high transmission, and another stuck in the up position that has the designed low transmission peak. Since these are two separate devices, but taken together, it shows the potential of this design approach if we can improve our fabrication precision. So in parallel with the MEMS device, we've also been looking at parametric designs of the actual filter, the metastructure, and using those for imaging experiments using static, non-switchable filters. This is because the MEMS fabrication process is relatively long and involved. So in order to accelerate the proof of concept, we did some parametric design of the meta surfaces. So we picked several different types of unit cells and arrayed those in the plane on sort of 100 micron small coupon scales on a single wafer. And we parameterized the lengths and widths and spacings, et cetera. So we ended up simulating, then fabricating and measuring over 100 different designs, and down selected based on those results to this double cross or sort of nested cross design as the most appropriate for our chemical sensing application. And this shows the sort of diversity of wavelengths available in a single layer. These are all fabricated on the same chip, on the same germanium chip, just varying the geometrical parameters lithographically. And this is a small subset of what we made of these nested crosses, just so you can see all of the different peaks available. And there's quite a few more there by tweaking the geometry. You can hit just about any wavelength you like in that 2 to 11 micron range. So here's a subset of those fabricated devices in the long wave. In the long wave infrared, we tuned our model a little more, and as you can see, we're getting very good model match to experiments. The model is the dotted line, and the experiment is solid. Below about 11 microns, and there we think that we're getting some loss due to the anti-reflective coating on the germanium wafers. But one of the strengths of this metafilter is shown here in this graph. We measured the transmission peak with respect to angle of incidence of the light at the across the spectrum, and you can see all the way up to 50 degrees, which is the limit of our measuring apparatus. You get no shift in the peak wavelength. There is a little bit of change in the transmission peak height, which is again due to the anti-reflective coating. But unlike interferometric filters, there's no wavelength shift, so that's good. This is a good filter for a wide-angle application. So finally, we did some mid-wave imaging performance through single large area metafilters, and this shows here a scene without the filter and then a scene with the filter. You can see that there's a little bit, the scene is a little bit darker. We had to increase the integration time slightly due to the roughly 50% in-band transmission that we get with the metafilter, but it's an acceptable level of attenuation. We are confident that we can do imaging with these, and then the next extension will be actual chemical detection, which is coming soon. So in conclusion, we've made some transmissive metastructures that are actuatable with MEMS actuators to switch the filter characteristics. We have some more work to do in terms of improving fabrication tolerances to get the precise design operation, but they do modulate the transmission bandwidth and the amplitude both. We're also looking at designs that will be more robust to fabrication tolerances for future work. We did a parametric study of over 100 metasurface designs to optimize performance for chemical detection, and demonstrated mid-wave IR imaging through a large area filter. Long wave is coming soon, and chemical detection as well. And that's all I have.